This is the Ocean Current Energy Generator presentation. I'm Derek Kabanka.
Brady Russell.
Sempre Rosa Variado.
And Philip McDaniel.
This is the outline for our presentation. We'll start with the background of our prototype. We'll give you some of the theoretical background behind it and how it works. We'll show you our designs and simulations and our task and timeline to show you how we fared on the project and our cost. And then we'll finalize with our conclusions and recommendations. So the problem statement is that there is a growing focus on renewable energy in today's world. There is so much emphasis on solar and wind energy that ocean energy often gets overlooked. Our goal is to harvest the energy from the ocean currents. Our project uses ocean currents, specifically tidal currents, to generate its electricity. The tidal currents are very predictable. They happen at the same, or not at the same time, but they happen 4 times a day, and we know when they're going to happen, and we know when we will be able to harvest that energy. Our objectives are to make this design easily transportable to use in recreational purposes or emergency situations. So it can be carried easily by 1 person or 2 people to put together and take it to the location where you want to test. Our motivation is to reduce the pollution and create a clean source of energy and to make this a portable device. So some background behind our project. These are 2 previous patented designs. They are similar to our project in the fact that they use a horizontal axis turbine design to generate the electricity. However, the design on the right is anchored to the floor, which makes it not portable. Ours will differ by not being anchored to the floor, and it will be portable. Another difference in our product is that it is all electrical components are housed above the water. As you can see in these 2 designs, it is fully submerged in the water, which leaves it susceptible to corrosion and damage to be applied to the electrical components, which could cause failure to the prototype. So for a little bit of theory on our project, the total amount of power that we can generate can be calculated with the values of the generator efficiency multiplied by the density of the seawater times the turbine sweep area of the turbine times the velocity of the water squared over 2. So we know the values for the turbine sweep area. We have a 30-inch turbine blade, which converts to 0.456 meters squared area. The velocity of the water we tested to be 0.274 meters per second at a depth of 0.549 meters. And the density of seawater is 1,029 kilograms per meter cubed. So we know those values, and our only value left to find is the efficiency of the generator. That can be found by taking the output power of our generator, dividing it by the input power, and multiplying it by 100. The output power can be found by taking the torque times the angular velocity of the generator, and the input power is equal to the input velocity times the input current to the generator.
Here we have our final design. For our design, we decided to use a V-belt and pulley system. This is what we're going to be using to harvest the kinetic energy from the ocean's tidal currents. Our turbine blade, we decided to go with a 30-inch 3-blade turbine blade that has a 20-degree pitch angle. This was, after a lot of research, found to be the best and most efficient for our electricity production on this design. We also implemented several things onto this design to make it unique. We added a navigational beacon up top to follow the standards for having any type of structures on intercoastal waterways. We also implemented in a reflective striping on the bracing of the legs. This just gives an extra safety precaution for any boaters or anybody that's using these waterways to be able to see our device out there. Here we have our dimensions for the project. So we decided to go with a 6-inch steel plate for the feet This steel was used rather than aluminum to kind of help keep this design from being top heavy. We wanted to really anchor it down and have a good center of gravity there. So we also implemented in small holes for doing sand spikes or anchors into the feet. So if needed, we would have that option to be able to anchor it down with heavy currents, just to prevent any sort of environmental pollution. So we wound up using 1/4-inch diameter bolts that were 2.5 inches long. We use this pretty much throughout the entire frame, and this is what we used to hold this entire project together. We used a wing nut design, which is very simple to take apart, very easy, and it also helps really ensure that we have that portability factor that a single person can take this apart and take with them. So our overall design height, we have a maximum with our legs fully extended, maximum height of 67.64 inches, and a minimum height of 60.38 inches. We have this 7 inches roughly of variability in our feet. We chose this design to kind of help give us that advantage on uneven terrain. It kind of helps us to keep this nice and level while the turbine blade is spinning. We used a 5/8 inch aluminum rod as our shaft. It was connected to our turbine blade, which then also has a 6-inch pulley connected to it. Our 6-inch pulley was connected to a V-belt up to the top where the generator is housed. There it has a 3-inch pulley system connected to it, therefore giving us a 2-to-1 ratio on our V-belt system there. Gives us a little bit more speed to help produce a little more electricity. So we've also used an 1/8 inch aluminum sheet up top. This was a lightweight material, yet it was strong enough to be able to mount our generator and other electrical components such as the battery, the navigational beacon, and other items that could be implemented onto this in the future. So we also created a housing up top. This was an acrylic housing. This is not waterproof, but it was water resistant. Our main goal here was just to kind of shield our electrical components from corrosion. Although sort of inevitable in saltwater environments, this is definitely going to help slow down that corrosion and kind of keep the elements off of it, such as sun and rain. So this was a lightweight, easy method to kind of take care of that. We also did a 3D printing for the hinges and for the handle. This would just prevent corrosion with it being a plastic material. It doesn't support a lot of weight. Our main component for this entire design was 1.25 inch for the frame and inch hollow square aluminum tubing for the bracing. On the picture here to the right, you can actually see our adjustable feet. We just did a double wire safety pin, which allows easy adjustment of each individual foot to allow for that uneven terrain. Here we did our FEM analysis on our design here. We applied a 50-pound force to the turbine blade, which then shows how much stress we have on our joints where everything is connected. Our bolts that we have were rated for 7 KSI, and we never got above 2.6 KSI on our FEM here. So overall, it was it was a very small worry that we would have a structural issue with this design. Here we have our demonstration of our actual prototype. You can see the blade is spinning, which is therefore spinning that V-belt connected to our generator. As this spins, it produces electricity. And we've also got some corrosion preventative. The paint on this is actually going to help kind of slow down that corrosion rate and prolong the life of this prototype.
Implementation. On your right side, you can see a picture of Packery Channel. We chose the location because it's easier to access and it was easy to test. We were able to test the flow, the current, by using a flow meter with the help of Dr. Zhang. Our prototype is able to be tested at max of 6 feet and minimum of 36 inches. Testing the results. Determining the generator, various tests were conducted to calculate which performed the most power and which would be more effective. Indicator's voltage was read through an in-line voltmeter. Results were analyzed through a charging period to ensure current, voltage, and temperature of the generator operates under a safe condition. On the right side, you can see 2 of my colleagues testing the flow rate. On the left hand, you can see a simulation that was conducted on EEDA. The bridge rectifier is the heart and soul of the circuit. It makes sure, it ensures that the flow of the electricity is going the correct way. On the right-hand side, you can see a rough test of how we tested the generator to pick which one we were going to stick with. The generator was able to produce 21 milliamps at 120 rotations per minute. The energy is stored into a 6-volt battery of the duration of 12 hours, depending on the velocity of the current. This is our task and timeline. In yellow, you would see our milestones, and the first milestone is the initiation phase, where the initiation was completed. This is where we select the project and continued on to the planning phase. The planning phase is where we research a lot of patents, analyze costs, set initial budgets, and was able to look into more into depth of different designs. Following into execution phase, this is where the group was able to test the current of the pack-free channel and test electrical components. This is also where you can assemble. This is where we were able to assemble the components and test the prototype. Budget and resource. This is where we have four. We were able to have 4 materials in kind. The first one was 1-inch hollow square tubing. The other one was a 6-volt battery. It was a 10-inch circular steel plate. We had 4 of those, and 2x2 aluminum sheet. This brings our cost to $254, and overall total cost of $23,254. The most expensive component that took a lot of our money away had to be the blade, which came out to $72. Standards, IEEE standards. The first one was charging and testing evaluation of lead acid batteries. U.S. Coast Pilot 5, Chapter 3, structures on or near channels must have white or red lights or a reflective material. Since our prototype does not exceed a certain limit, we were not needed to obtain any permits.
Here you can see our earned value chart. Here the orange line is the actual, the blue is our planned, and then the gray is our earned value. Starting out last semester in our planning phase, everything was on schedule and within budget. And then when it came down to mid-March, right after spring break, once the coronavirus pandemic hit, we began to start going over budget and behind schedule. Now for our risk management, we believe, so most of our risk came from being out testing in the water, in the environment. With that, in electric components, electrocution was a hazard, along with water hazards flowing through the water, along with polluting the environment. Something came off of our device and was washed away. We also had batteries could have overcharged or gotten overheated. And saltwater corrosion was a big risk that we plan on preventing, and with money we can prevent more, along with going over budget. Now the biggest thing was the environmental conditions. With that, the weather, and the main thing was coronavirus, making the project go over budget and behind schedule. Along with weather, if the weather was bad while we were testing, we wouldn't be able to go out and test. But to manage some of these risks, we had alternative solutions set up for if the weather is bad. We had other channels we could go to other than Packery channel if Packery channel didn't have enough current. But the weather's bad, then we could use electric motor to spin the fan blade to test the energy produced by our generator that way. For the coronavirus pandemic, we followed the CDC guidelines and the school's guidelines to staying away from each other and not spreading the disease. Along with that, we analyzed our progress throughout the entire project, and we tested in multiple scenarios, and we also self-quarantined ourselves and worked mostly off of Zoom like this. For our global impact, this project will benefit society in the fact that it helps get away from using fossil fuels and using a renewable resource. Currently, renewable resources are on the uprise, And that is mainly because fossil fuels are starting to become depleted. Researchers believe that within the next 115 years, we will be depleted of fossil fuels. And so the market for renewable resources are not only on the rise, but should surpass one of the biggest industries in the world of fossil fuels. This will also be better for the environment. Fossil fuels produce CO2 pollution and are harmful to the environment around them. But with our design, it will just sit in the channel and not affect the environment around it, and also keep us from using these harmful energy resources. And for the economic, for full scale production, it will in the long run be cheaper than fossil fuel energy resources, and the demand over time will only go up. And for a conclusion, our OCEG prototype is a small-scale production, energy production device used ocean currents to produce energy. The ocean does provide enough current for us to produce energy, and it is a very predictable source of power. The market will always go up, and at some point should surpass fossil fuels, which is one of the biggest industries in the world. And for our future, we hope that the future engineers could look at our design and hopefully improve upon the electrical aspect on it, and also the corrosion prevention. Hopefully with more money, you can prevent the corrosion that goes on through the saltwater air. And with that, I would like to conclude our presentation, and we look forward to the questions you have for us.